how does that help me to find the amplitude? Okay, how does that help me to find amplitude? Well, remember, kinetic potential plus kinetic has to equal to the maximum potential, right? And the maximum potential is equal to half Ka squared. That's how it's going to help me to find the maximum amplitude. So potential plus kinetic is 254.396, and that's equal to half times 144 amplitude squared. So I get 72. So divide my answer by 72. Okay, and then square root it. So divided my answer by 3.55 and then square root it 0.5. The amplitude came out to be 1.8797 meters. Let's see if that makes sense. So the general equation of motion now is going to be what? My x equation is going to change. It's going to equal 1.8797 sine of, right, omega is going to equal what? Omega, my new omega, I have it here, 4.89897 t plus phi. Right? Now we have the x, this is the new amplitude. The new amplitude has decreased. Does that make sense? The block was going to the left, this block came, embedded itself, it made it heavier, it kind of fought against it, right? It made it heavier, and so now the system has more mass, and it's not going to compress and stretch as much, because originally its amplitude was 2, right? This time it's not going to, it's only going to compress and stretch by 1.8797. This is the new omega, so it went down from 6 to here. What's my new phase angle that I should describe? Okay? Well, right now let's keep that as it is. The v is the derivative of this, so I take 1.8797, multiply it by 4.89897, and I get 9.2086 cosine of 4.89897 t plus phase angle. And then the acceleration is the derivative of that, which is you just multiply that and you get something sine, okay? So the best way to get the phase angle is what? We know the initial velocity right after the collision, right? The initial velocity, well, I erased it here again, but the initial velocity was negative 2.329 meters per second after the collision. I should even say the final velocity, because the initial was the block without the collision, and then the final is right after the collision. So when I put t is equal to 0 into my new equation, right, this is my new omega, if I put t equal to 0, I should get that. Negative 2.329 is equal to 9.2086 cosine of phi. Okay? So again, what phase angle will satisfy that? So you're going to do negative 2.329 divided by 9.2086. You're going to get negative 0.2529 is equal to cosine of phi. And then you take the inverse cosine. Is going to be 1.8265 radians. So it takes that many radians. This is the second quadrant basically. It takes for the phase angle to be this in order for the cosine to be negative. Now, what would sine of that be? Sine of that would be positive, all right? It's in the second quadrant, so it would be positive. So it would yield positive for this. So now I get here phase angle 1.8265. Let's put it into here. 1.8265. 1.8265. Okay, and now if I check the initial x after the collision, sine of 1.8265 times 1.8797. What's my initial x right after the collision, or which is what I called x final, right? 1.8186 meters. That should equal to the initial position of the block when the other block hit it, right? Because it didn't give it, it didn't bump it. What was my initial position of the block? 2 sine of 2. 2 sine of 2. 1.8186 meters, 1.8186 meters, so it's the same. So we basically redid the whole thing. Everything changed. The new omega, this is the new omega, this is the new phase angle, this is the new amplitude, this is the new final velocity of the system, the maximum velocity of the system. So now we can answer any kind of questions about this. What's going to happen to the two system, the two block system? Energy has been lost in the collision because it is an inelastic collision, right? Very, very interesting problem. So you can kind of see example of how you would do something like this. Even a more complex problem would be if the block came, and then this was a block, and then the block came, and then it was an elastic collision. So there's a block with a spring here, and then another block came, hit it, bounced back, and it was elastic collision. And then you can analyze what would happen to that. So have fun with that. Okay, so you can see a really good example here of oscillatory motion and then combining it with momentum conservation. Thank you.